Common Lisp has many high-order functions like map, filter, reduce, but they usually work on sequences. What if you want to express a general computation? This is when the series package becomes useful. The series package offers basically some generators. So, when you generate a sequence, it doesn't actually take any space. And when you do some computation on it, it gets executed as efficiently as possible. Let's start by loading the series package and all of its symbols. We start with a simple task, summing the first n natural numbers. We can start with scan range and provide a big number. This is just a pretty print. It hasn't actually loaded all of the numbers from 0 to 1000. To get the sum, we just run collect sum. We can verify what series is actually doing using macroexpand. We can see that it is initializing a variable sum to 0 and the first number. Then number is increased by 1, sum is increased by number, and if we are over 1000, the loops end. This is the same code that would have been executed if we wrote the whole loop by ourselves. Instead of the sum, we can make the product. This is, we basically want to compute the factorial of a number. We start always with scan range, but this time we have to pay attention to exclude the number 0. And then, to multiply, we use the generic collect function, to which we have to pass the type of object we are working with, in this case integer, the first value, which is 1, the operator, which is the product, and then the range itself. One may think that this code is less readable than the previous one. So we define an auxiliary function, collect star, that basically does the product. This is not actually a function because the series package overrides also the CL symbol in order to optimize this kind of auxiliary functions. Then the factorial function is just collect start of scan range from 1 up to n. From the expansion we can see that the result is actually again very similar to what we would have got if we wrote a loop. Series are lazy. We get the value only when we need it. For example, scan range represents the whole set of natural numbers. People familiar with lazy languages like Haskell may see this idea familiar. But the list of natural numbers is a boring series. What about the list of Fibonacci numbers? To get it, we can use the generic scanfn. In this example, scanfn will generate two series, both of integer numbers. The first number of those two series are 0 and 1. The next number of the first sequence is got by the second, while the next number of the second series is the sum of the number of the two series. Then we assign it to a variable f. In particular, the second series will be thrown away, and f is actually the first series generated by scanfn. We can see that the values of this series are actually the Fibonacci numbers. Then, for example, we want to write a function that computes the sum of the first n Fibonacci numbers. Using what we have just learned, it is quite simple. We start from f, we get the first n element using subseries, and then we collect sum. We can see that a warning is shown because it could not really optimize the resulting series. Let's try to sum the first 1000 Fibonacci numbers. The same problem could have been solved also using this function, in which we have two variables, predecessor and successor, to compute all the Fibonacci numbers, sum that will contain the final value of the sum. We use the time to repeat the loop for n times. The loop will return the variable sum, and we use a parallel setf to update to the next iteration. Let's try to do the same computation. We can see that the time is absolutely comparable. It's the same order of magnitude. But if we look at the function, the one used in series is much more readable. The one with loops contains a lot of logic mixed together, from how to compute the Fibonacci numbers to how to compute a sum and initialize the variable to 0. The standard way to learn about the series package is the appendix of the Common Lisp Language 2nd edition. As usual, one has to pay attention on what to optimize. The first goal is always to write the code as clear as possible. When there is a bottleneck, one has to run some performance test, understand what is the problem, and re-optimize what is needed.